Hello, I'm Shota Yamanaka from Yahoo Japan Research. In this study, we empirically compared two methods to predict error rates in target pointing tasks. In a conventional method to predict error rates using a mouse and 1D targets, we assume that click point variability sigma linearly increases with the target size W. Then we can compute the probability that a click falls outside the target using the Gaussian error function. So we need two steps, predicting the endpoint variability sigma and computing the error rate based on the target size and predicted sigma. These two steps have also been applied to touch-based pointing with 2D targets. For a 2D target, endpoints form a bivariate normal distribution, and the x and y coordinates independently increase with the target size. Then we can compute the error rates in the same manner. The focus of this study is to predict error rates as accurately as possible. Accurate error rate prediction can contribute to user interface designers and researchers. For example, we released this tool for the designers in our company. When they configure UIs in smartphone apps and web pages, they can determine the target sizes based on the predicted error rates. Another example is the typing speed prediction model. According to Banvik and colleagues' model, the typing speed gradually changes depending on the error rate when users tap a key. Therefore, to predict the operation speed accurately, a good model on error rate is needed. In this study, we compared two methods. One is a conventional two-step approach. For this SD-based method, the error rate prediction is a byproduct because the parameters A and B are optimized to predict the sigma. In contrast, we found that integrating these steps gives better prediction accuracy. That is, we determine the parameters A and B so that the observed error rates match the right-side values. In this process, the parameters are optimized for predicting the error rates. This ER-based method has been used in previous studies, but an empirical comparison of these two methods has not been formally conducted. We compared the two methods with our 8 datasets previously published. We want to strengthen our claim that the ER-based method robustly outperforms the SD-based method within the context of the most general case of target pointing, static target acquisition. Therefore, we tested various conditions regarding target shape, movement direction, input device, experimental environment, and sample size. Testing other tasks is included in our future work, such as pointing in virtual reality environment, moving targets, temporal targets, goal crossing, and path steering. The ER-based method determines the parameters so that the R-squared and mean absolute error values become the best for fitting the observed error rates. However, because the ER-based method uses a nonlinear regression, sometimes we obtain bad results depending on the starting values and parameter ranges to be searched. Hyperparameter optimization (HPO) can solve the starting value problem, which iteratively searches for better parameters. And giving extremely wide ranges for the parameters is sufficient, because HPO will find better parameters as the iterations progress. So we compared two variations of the ER-based method. One is using the default setting of Python's nonlinear regression, and the other is using HPO. We explain the results of 3 datasets in this presentation. The first experiment is the simplest task of 1D target pointing. When we use all fitting points, the SD-based method shows a good R-squared, but predicts higher error rates than the observed values. In comparison, the ER-based method doesn't have this problem. We also test leave-one out cross-validation to analyze if the ER-based method can predict error rates for future target conditions. The results show that the mean absolute error and root mean square error are smaller than 0.5%, which are better than those for the SD-based method. Next, experiment 2 used rectangular targets. Interestingly, the ER-based method with the default setting shows consistently high error rates of up to 90%. Manual tuning of parameters to resolve this problem is costly, but using HPO automatically resolved this issue. Experiment 3 used a smartphone as the input device. The default ER-based method shows a negative slope for the regression, which means that the predicted error rates decrease as the observed values increase. Although we obtained a large R-squared value, this is meaningless, as we cannot predict the error rates accurately. In addition, for the leave-one out cross-validation, the default ER-based method sometimes yields negative values in the square roots. In this case, we cannot compute the predicted error rates, and thus we note NA. In contrast, using HPO can determine meaningful parameters, and we obtain more accurate prediction results. In the same manner, we confirmed that the ER-based method with HPO outperformed the SD-based method for all 8 datasets. However, the ER-based method has a clear limitation that the parameter values are sometimes inappropriate in accordance with human motor behavior. For example, in experiment 3, we obtained B equals almost 0. This means that the tap point variability on the x-axis is constant regardless of the target size W, which is inconsistent with previous studies. Because our goal is to obtain a good accuracy to predict error rates, this result is acceptable. But we are aware that parameter values play an important role in understanding human behavior. Some previous studies have claimed that the optimized parameter values are consistent with existing reports on human cognitive models and performance models. So our current study is positioned on the accuracy improvement side. To conclude, we empirically confirmed that the ER-based method with HPO achieved the best prediction accuracy in the all data analysis and cross-validation for the 8 datasets. In comparison, the default ER-based method sometimes shows the same results as using HPO, but other times it showed meaningless results, such as extremely large error rates and negative correlations between the observed and predicted error rates. Therefore, always using HPO is a safe choice, and HPO is needed to exploit the full potential of the ER-based method. As a limitation, the parameters are optimized to predict error rates accurately, and might be inappropriate for understanding human behavior. So the ER-based method is useful for those who want to focus on the accurate prediction of error rates, such as user interface designers. That's all. Thank you for listening.